Hey folks, and welcome to the back half of Module 11. Just like some of our earlier modules, this one isn't particularly long. It does involve some complex material, but again, we mostly focus on understanding it conceptually. So, in the last couple of videos, we talked about repeated measures, ANOVAs, which happen again when you have a within participants design, 3 or more samples coming from one factor. Again, make your flowcharts when you're studying. I will be asking you to select the appropriate tests for different research designs and to tell me how you know that it's the appropriate test. Again, it's not something computers can do, so it's heavily emphasized in this course, and you are going to be asked about it. But anyway, those repeated measures ANOVAs, 3 or more samples differing on one factor, and again, using a within participants design. Now we're going to talk about our cases when we have multiple factors in a between participants design, and we use what are called factorial ANOVAs. So here's the gist. Again, we have 2 ANOVAs in our pocket. The one that we talked about at length was the one-way ANOVA with a between participants design. Then we talked a little bit about repeated measures ANOVAs with a within participants design. Now we're going to talk about what happens if you want to look at more than one IV or quasi-IV at the same time. A lot of times we want to do that, both for efficiency's sake to get data on multiple IVs, but also to see if those IVs influence each other, if they appear to if the relationship between the IV and DV changes based on the level of the other IV. That's something we want to look at. A really easy example would be take an existing effect and see if it works differently for men and women. So that's a second quasi-IV, and we are looking at whether or not the established effect of an IV on a DV is different for men versus women. So that would be multiple factors. So other examples, we might want to measure people's depression levels. We want to see the actual effect of antidepressants. So we have 2 different antidepressants. We have a placebo and a condition where they don't get any pill at all. Again, a placebo is usually a sugar pill. But we also want to know the effectiveness of people's expectations. So we manipulate what they're told about the treatment. Half the people are told, no matter what treatment they got, that it is highly effective in changing depression. The other half are told it's moderately effective. So we're not only manipulating what substance they're ingesting, but also what they expect it to do, what sort of effect they think it's going to have. Maybe we want to do a violent media study. We want to look at levels of aggression for people based on what sort of media they consume. So we, again, manipulate one factor. We have people either watch a violent movie, a drama, or a comedy. But we also want to look at the role of provocation, which oftentimes plays a really important role in whether or not aggression happens. So half of our participants, no matter what movie they watch, they're going to be provoked. The other half of our participants are going to be praised. We have 2 independent variables here, what movie people watch and their provocation. A lot of times just opinion surveys, like attitude towards the president or the government or specific policies, they will measure multiple quasi-IVs. They will measure people's party identification, Republican, Democrat, third party, independent, and they will also measure their gender. And we'll look at whether or not those relationships change between, say, party ID and approval for different genders. Again, we're looking at multiple factors independently. So can't use a one-way ANOVA there because, again, a one-way ANOVA requires just one single IV or quasi-IV. It only works for those between participants, between groups designs with one IV or a quasi-IV. Instead, we can use what's called a factorial ANOVA. A factorial ANOVA, again, allows us to apply that ANOVA framework to situations with multiple factors. The book, by the way, talks about this in terms of 2-factor ANOVAs. I don't like that term because a factorial ANOVA can accommodate 3 or 4 or 5 factors. It gets really complicated, but it can do that. So 2-factor is a little limiting, but they're describing the same process just with only 2 factors. Now, we're going to mostly talk about 2 factors, fortunately, but we will talk a little bit in the last video of the module about some situations with 3 or more factors. All right, so again, IVs and quasi-IVs, those are called factors. The number of factors in your design is the number of IVs and quasi-IVs that you have. One of the first things to know about factorial ANOVAs, because the designs get a little complicated, it can be a bit of a tongue twister to explain every possible condition. We've come up with a technique called the notation of these designs that lets us describe what sort of design is present. So when we have multiple factors, we create this little, it almost looks like a little equation that is sort of a shorthand for the overall design. So here's how notation works. I'll give you an example, and then I'll tell you what the rule is. Let's take our movie and provocation example. That's a design where our first factor, what movie people watch, has 3 levels. They watch a violent, dramatic, or comedic movie. And our second factor, the provocation, has two levels. They're either provoked or they are praised. We would call that a 3x2 design. The reason why, there are two factors, so there are two numbers. The specific numbers tells you how many levels each factor has. Factor number 1 has 3 levels. Factor number 2 has 2 levels. By the way, it would be equally valid to call it a 2x3 design. That's a little less common. Usually we put the bigger number first, but both are totally fine. They both are describing those essential elements, that there are two factors. One of them has 3 levels, the other has 2 levels. So we know a lot of information about a basic design just using this little equation. We know that this has 2 different factors, and we know how many levels each factor has. So that's a nice way of summarizing, again, these factorial ANOVA situations, which can be more complex. The null hypothesis stays the same as our one-way ANOVA. We're again running hypothesis tests. We're again using F ratios to test them. The null hypothesis is that all the populations you're comparing all have the same mean. The alternative hypothesis, again, that generic statement, at least one population, has a different mean than the rest. Notice again, we reject the null. We're usually stuck with this kind of unsatisfying statement. So you are going to be running generally post-hoc tests here as well. One major change, because there are now multiple factors, there are multiple hypothesis tests being run, each of which can be significant or non-significant. We are going to talk in our next video about what kinds of hypothesis tests they're running and what it tells us about the data. But for now, we have populations. They've generally been represented by samples. That's still the case, but we have a special term for samples made up of combinations of different factors. Those sort of samples are known as cells. A cell is a unique combination of different levels of each factor. So for example, in our movie and provocation example, some people watched a funny movie and were then provoked. That combination of factors is one cell. Some people watched a funny movie and then were praised. They weren't provoked. That would be a second cell. Some people watched a drama and they were not provoked, they were praised. That's a cell, that people who got that exact combination of conditions. Another group of people saw a dramatic clip and then were provoked, and that is another group of people who experienced that combination of factors. So a cell is just the combined levels of the different factors that are present. You can find the exact number of cells in any study if you have the notation, just by solving the equation of the notation. Notice this looks like a little multiplication problem, a tiny little one. 3x2, there are 6 different cells, and you could list them all out if you wanted to. Might not be a bad exercise if this is tricky. Find all 6 combinations of movie type and provocation. If we added another factor to each independent variable, or another level to each independent variable, we would have a 4x3 design, which would have a total of 12 cells. So again, just adding one extra condition or level to each IV, we would now have 12 cells. Things would get very complicated very quickly. All right, wrapping things up with some basic assumptions of a factorial ANOVA. Again, we have 2 or more IVs or factors with independent samples, with a between participants or between groups design. So I mentioned earlier there's a branch here that hasn't been filled in. What if you have a within participants design and you have multiple factors? Well, there is such a thing as a repeated measures factorial ANOVA. This is the entirety of what we're going to talk about it, how we'll talk about it, because they are extremely rare. Those order effects get really, really out of hand when you're manipulating multiple factors and measuring people perhaps 6 times, perhaps a dozen times. It gets out of hand very, very quickly. We assume that we're taking a random sample of, again, interval or ratio scores. Our DVs still have to be interval scores. That's been true for every single test, interval or ratio. So we're assuming that those samples are randomly drawn from their respective populations, and that the DV follows a normal distribution in each population. Again, as we've seen, that's a pretty safe assumption because of things like the sampling distribution. Finally, we assume every cell, that the population that they come from, has similar variance, that they, again, don't vary in a substantively different way. Just like our earlier test, though, if these assumptions are violated, we're still in pretty good shape. It still is what's called a robust test. So that closes off our introduction to factorial ANOVAs. The next video, we are going to be talking about the different sort of effects that can happen and the different hypothesis tests that correspond to them. We'll be talking about main effects, which you've already seen before, though not with that name, and interactions. I will see you there.